Welcome to the second presentation from the Information Systems and Semantics series, which is about representing metamodels, models, and data in RDF format. In this presentation, first I will quickly recap RDF basics from the previous one. Then I will explain the view on metamodel, model, and data relevant to use of RDF, which will lead us to taking a look at RDF schema and the web ontology language, which is abbreviated as OWL. I will then show how to make models using these, and then also how to create metamodels. Finally, we will take a look how existing ontologies can be used together with our models, and also how to make validations using something called RDF shapes. RDF uses statements or semantic triples to describe practically any resource. Such a statement has form of subject, predicate, and object. Eventually, we also have quotes with fourth element capturing a context. A resource may be some literal value or referent, which is something with assigned identifier. And there are various formats for serializing or representing the RDF statements. On the slide, on the right side, we can see an example in the turtle format. When taking a look at the example on the right side, we can go through it. So there is some subject. This is some identifier representing the resource if. Then we have some predicate, in this case has name. And finally we have object if as a string, literal, some value. But looking at this example, there are many unclarities, right? For example, what is if? What predicates can we have about if? But also, what is the meaning of has name predicate? What can be object there? What can we have? Can we have more names for the resource if? As this example is using clear and human understandable identifiers, we can roughly get some ideas what it means. But RDF gives us flexibility, and we could basically do any triples that we like. And it is then a question how to also capture like the meanings behind these triples. To motivate you a bit more that we actually need some semantics, there is yet another example using Wikidata, which is a resource similar to Wikipedia but created using semantic triples and practically forming a huge RDF graph. And they, as you can see, use such identifiers for entities and properties using these letters and numbers. And actually, by seeing this, you don't know what that is, what it means, and what it actually says. So to break this down, the subject is Prague, a capital city and a district. So it's something that can be part or capital city of some country. Then the property, the predicate here, has meaning capital of. And finally, as you can expect now, the object is a country, it's Czech Republic, and as such, it can have cities as capital cities. So it actually makes sense to use it as object for some statement where the predicate is capital of. But how we actually capture the meaning of these triples. For that, for getting the semantics for such a triple, we need to provide some model where it is stated that capital city is a class, that part of or capital of is some property with some certain constraints, such as that subject must be some city and object must be a country. And finally, country is again some class. And in this model, we are explaining for both humans and machines what it is, what are the constraints and possibilities related to these semantics. But we can go even further to the metamodeling level, specifying what is a property and what is a class. And using the triples, we can do all of these. So we can specify that something is a city, something is a class, something is a property, and all that while keeping all these expressions, all these statements in the RDF format. That only further shows the versatility and flexibility of this technology of semantic web. To create such models and metamodels, we need some ontology language, some resources and properties that can be used to form statements specifying a model or a metamodel. So for example, if we want to state that Eve is a person, we need to define person as a class. But then we need to get this resource or notion of a class from somewhere where it is clearly defined with proper semantics and accompanied by constraints and some rules. Such a place or metamodel or some container of expressions is RDF schema, or RDFS for short. It is a simple ontological language for RDF, and it allows us to specify types of resources, so classes, and then their properties. So it defines what is a resource, what is a class, literal, data type, property, and so on. So basically, all these things that I explained to you mainly during the previous presentation are defined in RDFS specification. What may be interesting that RDFS specification itself is purely in RDF, and also it's defined using terms of itself. So you can then observe there some meta-circularity on this modeling level. Basically, when you are investigated this RDFS, you need to check these two ontologies or vocabularies, one for RDF and one for RDFS. But these two are really closely interlinked together and using the terminology from one of the other. Actually, by visiting these links, you can directly see the RDF statements that specify those ontologies and how they actually define these things. So you can see their definition of resource, which is in other words class for everything. You can see a definition of a class, of literal, data type, property, etc. But there are of course more things covered in these RDF and RDFS ontologies, and there are also some properties that can be used as predicates then in the triples, so in the middle element of a triple of a statement. For example, this RDF type for stating that a resource is instance of some class, or domain and range predicates to specify subject and object classes of a property. And then there is also possibility to define subclasses and subproperties. So for example, you could have man or woman as a subclass of person. Finally, there are also properties for describing resources in human readable way. So some label, comment, or description, link to further information. This is this see also. And also some link to the ontology or dataset where the resource that you are describing is specified. So actually some backlink to the specification. Here is a short example for our simple example ontology, where we have a class person, and two subclasses man, woman, and then there is finally a property has name. So we can see that has name is of type property with domain person and range XSD string, so some string data type. So we are here stating that a person can have a name which is a value of type string. You can also take a look at some of the existing and widely used ontologies that are specified in RDFS, and you will see some documentation, usually some website, but you can also take a look at the RDF statements, how they actually specify the model using the RDFS. It may be at the first a very good source of some inspiration when you are starting to do the modeling using RDF schema. Another language for modeling or creating ontologies is the Web Ontology language, abbreviated as OWL, and it is actually a family of languages, not a single language, and it provides more options when compared to RDF schema. That is very simple. And it handles, for example, multiplicities, that something is required, class equivalence and property equivalence, some constraints such as disjoint complete, and many more. There are actually more versions of OWL, of this language family, and usually when we are using OWL we mean like the latest version, but just for your information there are multiple versions developed over time. There are basically 3 levels or sublanguages, and OWL Lite allows you to create simple class hierarchies with some basic restrictions. Initially it was designed so it promotes adoption of OWL in tools and to be really simple to implement. But nowadays you usually do not limit yourself just to use this language. Rather you would use OWL DL, where DL stands for description logics. And the key properties here of this language are completeness and decidability. So if you have an ontology using this OWL DL and some dataset using that, you can then always state whether a new statement is true or not, according to the dataset that you have, and also if it can be derived from the existing one or not. When talking about deriving, it applies things like subclassing, but also transitive properties, inverse properties, etc. Basically, this OWL DL does not allow certain metamodeling feature of OWL. But if you need metamodeling, you are going into OWL full, which loses the decidability for this, and processing of such ontologies may be a bit slower in various tools when compared to OWL DL, as this OWL full adds some additional complexity, mainly for the allowing of metamodeling. So the class when you're defining some class, it can be instance of some other class and stuff like that. Here you can see a visualization how the languages of OWL and profiles are overlapping, and also the difference between OWL 1, the older version, the newer OWL 2 on the right side. So you can see that they dropped OWL Lite actually, and instead they have these profiles. And you can see also the relation to RDF schema, which is just a subset of the OWL full, but also the RDFS has something that is not included in OWL 2DL and OWL DL, and that's something that is related again to metamodeling, because metamodeling can be done just in RDFS. You don't actually need OWL for that. Again, we have some example of OWL ontology. That's for the same thing that we had in RDFS. So you can use here OWL class, but actually it's really similar to RDFS class. But with this one, you could do such things as disjoint classes, additional constraints, cardinalities, and really many more. So this is how you can make actually some models in RDF, in OWL, and in RDFS. Now to get to metamodels. You can always take a look how RDF, RDFS, and even OWL are defined purely as RDF triples, RDF statements, and they themselves provide metamodel for you to write your own models or own ontologies, but they serve also as metamodels for themselves, but also for your metamodels. And of course other metamodels, not just yours. And you can see that in RDFS, that for example RDFS class is of type RDFS class, so you can see the circle here. You can also see there that RDF property is also RDFS class. RDFS subclass of as some property, because you want to use it as predicates in the statements, is of type property. OWL class is of type RDFS class. But here is maybe something interesting, that OWL class is also subclass of RDFS class. And it actually means that you know how to make instances of RDFS class, but if it's already something an instance of RDFS class, you cannot make instances. So now you need to also state that you are subclass of RDFS class to be able to make instances. With that knowledge, we can define our own metamodels, our own language to express some models. So for example, in the NS metamodel, there is something called data element. And we could here state that it's a class, but it's also again a subclass of a class, so we can make instances of data elements. And then for, of course, some documentation, we can state that it has a label data element, in this case in English. We can also define some property. For example, each data element, instances of this data element class that we defined, need to have some name. So we could define a data type property like this, and then data type property means that actually the values or the objects, when this is used as a predicate, will be of some data type, so those will be literals. And then we can state here the domain, so you can use this property for data elements, and the objects will be strings, and then this property has some label and its name. So here you can see that we have a human readable, or it can be also machine readable name as a string, And then we of course have the identifier in the namespace ns, and with identifier of inside data element dash name. So with such a meta model where we defined what is data element and what is data element name as property, we can use it to create models using that meta model. For example, here we create again person, but now not as a RDFS or owl class, but as NS data element. And we can also use the property here, NS data element name, to give it actual name, in this case person as a string. And we can see that we here comply with the ontology or with the meta model. So example person is some data element, so it's the subject of the data element name, and the object of data element name is some string. But before creating own ontologies and metamodels, you should always consider to reuse some resources rather than defining again the same in your own ontology. Because if everyone would specify the same concepts in own ontologies, it would then block the interoperability of underlying data, because they would be defined using different models, different, for example, properties and classes. And eventually you may need to provide some mappings between those ontologies, but that's usually a bit complex. So it's better to take a look at this and good care of reuse during the design of your ontology or meta models. What you can also do is to use existing upper ontologies, so some ontologies with very abstract concepts that can help creating models and meta models. Some of those are domain specific, some are not, and some are related even to some widely known modeling languages. So here in this case, in this example, if you encountered OntoUML, which is extension of UML class diagrams with some additional constraints from UFO ontology, that can be also used in RDF. For example, as shown here, how you could express that a class, that something is a class with stereotype kind, according to the UFO and OntoUML. So you can see the expression as a 2 or actually 3 triples in RDF, and on the right side you can see how it would look like in the UML visualization then. And final short note in this presentation is about shapes. While we were making some schemas, models or ontologies, that allowed us to define some semantics with some related constraints. Shapes are a bit different. They focus on constraints, not necessarily some semantics or meaning, and these constraints can be used on some patterns in RDF statements to make some validations, for example. One of the options to use here is SHACL, Shapes Constraint Language, which is again W3C specification, and it allows to specify simple patterns or even complex patterns, potentially even recursive patterns, and such patterns are then matched to the RDF dataset, so set of RDF statements, and if there is some violation of the rules, it results to some validation report, and the validation report is not like some text or diagram or something like that, but it's again RDF, so you get the report back of the validation again in RDF. An alternative to SHACL is called shape expressions, and they are really similar, but shape expressions or sheks is more compact. It's very simple, limited, and not so extensible. And here I wanted to mention it just that you know what it is, that it exists if you encounter somewhere, because it can be also used to model some rules or specifications over RDF data. But when you are deciding what to use, you would usually go for Shackle due to its stable W3C specification and also all these capabilities, including extensions and higher expressivity of these rules. So to sum up, RDF itself is very versatile and you could write any triples as you would want to, and that's possible, nothing will stop you from that. But as a result, you would get something ambiguous without meaning, and to provide the meaning, ontologies and models are needed. RDFS and OWL provide means for specifying such models, and eventually also metamodels in the same way, again, all in RDF. Finally, we touch here also a topic of RDF shapes. We did not go into much detail, but basically the notion that something like also exists, because that's something that helps you to express some constraints or some rules over some existing models. It's somewhat similar from what you may know from UML and OCL, Object Constraint Language. So this is also some complement to models in RDF. Thank you for watching this presentation, and I hope it gave you again some more insights on how you can structure RDF statements and now how to also provide some semantics through models and metamodels. And next time we will briefly take a look at some more examples related to querying RDF datasets and other practical use cases.